So this is just for my AP Physics kids, okay? Average Physics kids, you're done. If you're watching this, you're just watching it for entertainment values. Okay, so here's the deal. So if you look at independent, dependent variables and that big sign in the back that says ethics is MA. So here I've got a track. Just up here. Okay. And we're going to use these tracks a lot. Okay. They're pretty low friction. They're not completely frictionless, but they're pretty close. Okay. So, and here I've got this little fan cart. And I can put that on there. And I'll let go of it. And it begins to accelerate, right? Mm-hmm. Then I can crank it up to warp speed, okay? And get more force. So if I were to draw this graph, I've got two data points. I've got the force from the fan, and then I have the acceleration. So which one is my independent variable? Bodie, what's my independent variable? Force or acceleration?
Acceleration.
That's my independent variable.
No,
Force is my independent variable. Why?
because you're changing it.
Yeah, that's one that I control. Do I have it on low speed or do I have it on high speed? So if I were to graph this thing, okay, I'm going to put force on my x-axis, and then I put acceleration here, meters per second squared. Okay? Now, here's the deal. Is this graph going to start at 0, 0?
Yes,
Yes, why?
because if you don't have any force, it's not going to accelerate.
Yeah, Mother Nature's a lazy prima donna, right? If I don't apply a force, guess what? I don't get an acceleration. Okay? Simple as that. True?
Mm-hmm.
So, but the more force that I apply, guess what?
More
More
acceleration.
acceleration I'm going to get. So this graph is going to go roughly like this. So let's say that, I'm just going to make up a number, let's say that I was exerting 2 newtons of force, and let's say that I was getting an acceleration of 4 meters per second squared. Okay, just kind of see how this deal would play out. So at this point, could I find the slope of the line?
Technically,
Well, you
yes.
need to.
Technically, yes, as opposed to a non-technical, yes.
Yeah, because you have 2 data points. You have
Yeah, I've got 0, 0, and I've got
2, 4.
2 newtons and 4 meters per second squared. True?
Yeah.
Yeah.
Everybody cool with this? I've got 2 data points. I can find the slope of this line.
Mm-hmm.
We're good, right?
Yeah.
Now, in a math class, you would go change in y over change in x, and you would take 4 meters per second squared minus 0 and divide it by 2. And now I'm going to go ahead and write that as kilograms meters per second squared. Okay? Okay? Because of the fact that I want to be able to cancel this stuff out. Now, in a math class, you would just say, oh, the slope is 2. And that's all you'd have to write down. The slope is 2. But in this situation, I want to figure out what these units are. So if you look at what happens, I actually get 2, and it's a little bit hinky, but I get 1 over kilograms. Okay? And it's like, oh, that's just a little bit weird. Okay, it's like, oh, 1 over kilograms.
Yeah.
That's outside your comfort zone. You're going, oh. But look at this. For now, pretend that that is gone. We'll get back to it. Pretend that that's gone. If you're in a math class and I said, class, here's x, okay? And I want you to write the inverse of x. What would you write?
X over 1.
1 over x, or
X to negative first.
x to the negative first. These two things are equivalent. True?
Yes.
Okay? The inverse of x is 1 over x. Now, let's say it didn't, but let's just say. Let's just say that slope had worked out to be kilograms. It's not, but let's just say it is. If the slope had worked out to be kilograms, what do you think the slope would represent?
The amount of kilograms being added to?
Well, you're making it difficult. What are you measuring in kilograms?
Weight.
No, not weight, no, mass, no, mass, no, no.
That's what I meant. Mass.
Weight is measured in newtons.
Newtons, yes.
Force.
Mass.
Kilograms is measured in
Mass.
mass. So the slope of this, if it was kilograms, you would say the slope of the line represents mass. Okay? If it was kilograms, the slope would represent mass. But because it's 1 over kilograms, then just like, because it's 1 over kilograms, we say the slope represents the inverse of mass. Okay? So if it had been kilograms, you would say it represents mass. Since it's 1 over kilograms, the slope represents the inverse of mass. Okay? Go with that. Okay. Now, if the slope had been meters per second, we would say the slope represents velocity. If the slope represents seconds per meters, we would say it's the inverse of velocity. But you won't know that until you begin to pay attention to the units of the slope. Okay? Now, think about this. We're going to play the what if game. I'm going to do the same thing again, but now I'm going to put a half a kilogram mass on it. Okay? So now, when I get that acceleration, what do you think is going to happen to the amount of acceleration now that I have that 500 gram mass on it?
It's going to decrease.
It's going to decrease.
It's a decrease. So this when you have more stuff, this boils down to Newton's first law of motion. It says objects at rest remain at rest, objects in motion remain at motion. We'll talk a lot more about that. But basically, the more stuff you have, the harder it is to get it to move. But once you get that stuff moving, it's harder to stop it. Okay? So once I put that 500 gram mass on there, and again, this is where you focus on what do you hold constant and what are you changing. So in this situation, I'm going to keep the same amount of force, but I've increased the mass. So if I go to this graph and I apply that same 2 Newton force, what's going to happen to my acceleration?
So it's going to go down.
It's going to go down, right? It's not going to accelerate as quickly. So if this is, hopefully this doesn't flip out. Okay. So now, instead of 4 meters per second squared, it might be 2 meters per second squared. So what's happened to the slope of the line? The slope of the line has become smaller because for the same amount of force, I'm going to get
Less acceleration.
less acceleration. So the slope of this line is, if I take 2 divided by 2, check my math, I get 1 over kilograms. The slope of this line was 2, and then 1 over kilograms. Now, this is where the magic happens, okay? And this is where you have to think this through like another step. So, listen to me very carefully. The slope of this line represents the inverse of mass, right? So if I were to take the inverse of mass, in other words, if I were to flip this over, if I were to take the inverse of mass, what do you think I would get? I would get kilograms, which is a measure of mass. Oh, so look what happens. If I take the inverse of this, I take 1 over 2 and 1 over kilograms. And again, this is where you have to pay attention to the units. So notice that my kilograms are going to flip up, and I'm going to get mass, which is kilograms. So notice that this mass is a half a kilogram, and if I take the inverse of 1, I still get 1. So this is 1 kilogram. So this is, and you can never see this hidden relationship if you don't pay attention to what the units are on the slope. So if you're going to plot force and acceleration, then the slope of this line represents the inverse of mass. So as I apply more and more force, I get more and more acceleration, this sloping line. But if I apply the same force to more mass, the slope becomes less, but the mass actually becomes bigger. But you'll never see that unless you pay attention to the units. Okay? Makes sense. Okay. Now, most of you have been through Chem 2. Yay, nay, some?
Yay.
Okay. All right. So we're going to spend a little bit of time, not a whole lot, talking about this concept of significant digits. Okay? So here's the basic idea of significant digits. Significant digits indicate how well you did in measuring an object. Whether it's mass, whether it's distance, whether it's speed, whether it's acceleration, time, whatever. Okay? So here's just a simple example. So when you all look at your measurements that you all made for this lab, okay, I've looked at some of it. Some of you, like when you were measuring, you had like 7.5 centimeters, okay? Some of you even went like 7.45 centimeters. And some of you just went 7 centimeters, okay? So precision is basically determined by the number of decimal places that you have. It's the number of known values. So when you look at a measurement, what's always assumed is the last digit is like an estimate. So this is what you all should have been able to do, at least when you were looking at what you were able to measure. You had like 7 and 8. These were like centimeters, okay? And then you had these marks in between, okay? So you could easily estimate one more decimal place than what you knew, okay? Easily. If you really wanted to get picky, you could have estimated, so let's say that that distance was right here. So you could have said, oh, that's 7.45 centimeters, okay? So here's the deal when you get into significant digits. All non-zero significant digits are like upperclassmen. They're cool, they're significant, okay, they count. So in this situation, you would have 3 significant digits because they're all non-zero values. These are all upperclassmen. Freshmen are like zeros. For the most part, they don't count, they're not significant, but we still need them, okay? So here's the deal. So let's say that you have 7.05 centimeters. So what's happening here is that you have a freshman that's cool enough to hang out with the upperclassmen. So if you have a freshman that's surrounded by upperclassmen, that's significant, okay? So he's cool. So this would have 3 significant digits, okay? Now, where you run into trouble is when the freshman is at the beginning or at the end of the line, okay? That's where you run into trouble with freshmen. Now, if this was 7.50 centimeters, so what we're saying here is that this 0 on the end is significant, and here's the reason why. Because if I just say it's 7.5 centimeters, that's a reflection of the precision of my measuring device. So if I just put 7.5 centimeters, that indicates that I know this number and I'm only estimating the tenths place. If I put 7.50, that says I know the 7, I know the 5, and this 0 is an estimate. So here's the deal. When you look at zeros, if there's a decimal place, you count everything to the right. So if there's a decimal place, here's a short version of this. It's the easiest way to remember it. If there's a decimal place, you count everything to the right. So in this case, this would have 3 significant digits. If it's 7.5000 centimeters, all of these zeros would count, okay? So if there's a decimal place, you count everything to the right. But if there's not a decimal place, and here's the good example. You say, okay, hey, what's the enrollment at Mays High School? That's about 1,200, okay? So let's say that that's my estimate of the enrollment at Mays High School. I'm solid on the 1,000. Okay, I know I'm somewhere between 1,000 and 2,000. The 200, that's just a guess, right? These zeros are like freshmen. They're taking up space, but they're not important. Okay, we need them because we can't say, oh, the enrollment is 12. Okay, we need those zeros, but they're not important. Now, notice here, there's not a decimal place. If there's not a decimal place, you find your first non-zero digit, and you count everything to the left. So, if there's no decimal place, you count left. If there is a decimal place, you count right. Okay? It's the easiest way to remember this. So, now here's the classic example of how this plays out. Let's say that you made that measurement on the lab, and your measurement was exactly 7.5. So you write that at 7.50 centimeters. You know the 7, you know the 5, that 0 is an estimate. This has 3 significant digits. Okay? Cool with this. There's a decimal place, 3 significant digits. Good with that. Now, here's the deal. Let's convert this into meters. Oh, okay, right? There's 100 centimeters in 1 meter. Well, I divide by 100, I get 0.0750 meters. Okay? All I did was move that decimal place over 2 places. So here's the deal. If this is the case, right? Now I have a decimal place, but now I find my first non-zero digit and I count everything to the right. So I find this 7, here's the first upperclassman, and I count everything to the right. So these zeros here are just taking up space. Okay? I don't count these, because if I count those, then I'd be up to like 5 significant digits, which would imply a higher degree of precision than what I have. So if there's a decimal place, find your first non-zero digit and count everything to the right. Okay? If there's, see, now here's the other thing. Let's put this in terms of scientific notation, right? So, quick, I know you all have been out of school for like 6 months. So let's quickly review scientific notation. If I were to put this in scientific notation, I'd move this 2 places. Anytime you do scientific notation, you have 1 decimal place to the left of, you have 1 place to the left of the decimal point. Standard way of writing things in scientific notation. So, I'm going to write that as 7.50 times 10 to the, now, is it to the negative second or to the positive second?
Negative second.
Negative second.
The negative second meters. Now, here's the beauty of scientific notation. In scientific notation, everything that you write is significant. You don't have to guess. So when I see 7.50 times 10 to the minus second meters, that has 3 significant digits. Okay? Now, here's the decision that you all have to make when you write down answers in my class. There's 2 decisions that you have to make on every answer you write down. One is, what units do I put? And the other is, how many significant digits do I put in your answer? Okay? Those are the 2 decisions that you have to make. Now, your book, and your assignment tonight is going to come out of your book. Your book, this is why I hate textbooks. So your book goes through and it talks about, oh, here's the rules of significant digits and all of this. But so many times, when your book gives you problems, it'll only give you, like, it'll say, oh, you know, the aircraft carrier is 50 meters long. Okay, well, here's the problem. If they write this is 50 meters without a decimal place, this only has 1 significant digit, which means technically your answer can only have 1 significant digit, which is just a bogus answer, okay? And here's why this is bogus. It's like, you're saying, what's the length of it? Oh, I know the 5, I estimated the 0. It's about 50 meters. It's like, seriously, you're going to build an aircraft carrier and you can just guess the length of the takeoff deck? That's about 50. Whatever, okay? No, you know you're going to have a higher degree of precision than this. So, and this is, I've met the authors of this book and I've chastised them. I said, for the love of God, you go through this whole thing to talk about significant digits, and then you completely screw up the answers. So here's just a general good operating guideline. On all the assignments that I give you, I always give you at least 3 significant digits. So when you do a mathematical operation, generally you just can't go wrong with 3 significant digits. Okay? It's just a good operating parameter. Some people get really picky about it, but here's the reason why that it's important. Okay? So let's say that we go out in the hallway, and I'm going to have Ryan measure. We're going to measure out 10 meters, and we're going to have Ryan run 10 meters. Okay, that's about 10 yards. Okay, and we know that's about 10 meters. It's not 10.0000. We didn't set up a laser beam and measure exactly 10 meters. Okay, we laid out a piece of tape and we said, hey, it's about 10 meters. Okay, and then we're going to stand there with stopwatches and we're going to time him as he runs by. Okay, and let's say we time him as he runs by and we get 1.82 seconds. Okay, just make up a number. So if Ryan ran 10 meters and it took him 1.82 seconds, we can calculate his speed, right? Simple process. We can take 10 meters, so somebody get out a calculator, somebody take 10 meters and divide that by 1.82 seconds. Now tell me what the oracle says the answer is.
5.49. Wait, do you want me to?
I'll keep going. Say
5.494505.495.
5 meters per second. Now here's the problem. And this is the overriding theme of significant digits. I can't make my calculated answer look better than the data that I have to start with. Because if you tell me this is Ryan's velocity, I'm going to think you all had some amazing timing devices. Okay? I mean, this was like, wow. I don't know where you guys got this stuff, but that's amazing. I mean, you know, tenths, hundreds, thousands, 10,000s, 100,000s, millions. You got this, wow, it's cool. No, okay? I can't write that number down because, and again, you all have this belief that the calculator, stop.
I think it's because I accidentally just hit your desk.
Okay, I do my Jedi mind trick. So, but it's like, honest God, it's like you all see your calculator as an oracle. And you feel like this moral obligation to write down all of the numbers that the calculator gives you. Because you think like the calculator is going to get upset with you and not give you the right answers if you don't write down all of the digits that it gives it. Calculator doesn't care, okay? So in this situation, I got 3 significant digits here. I got 3 significant digits in my time. I've got to write this answer with 3 significant digits. So if I were to write this with 3 significant digits, I would just write that as 5.49 meters per second, okay? So I can't write all of these digits because I don't have that good of data. If I got sketchy data, I can have sketchy answers. If I have really good data, I can have really good answers, okay? That's it. So that's the short version of significant digits. And if you just remember this, you can't make your answer look better than the data that you have to start with. Okay, now, we're going to do a lot of conversions. Let's just run through some simple conversions to make sure everybody's kind of cool with what's going to happen. So I'm going to go through the 2 most common conversions you're going to get. So let's say that we've got 112 kilometers, and we want to change that into meters. Y'all are going to do a lot of conversions. I want to make sure everybody's cool with this. So on the back of your yellow sheet, you've got the most common prefixes that you're going to use, okay? So like you got kilo, which is 10 to the 3rd, prefix of K. So, and again, when you're doing these conversions, keep me happy, okay? I'm guessing you all have been taught this factor label method. If you went through Mr. Shirt's Chem 1 or any kind of math class, you've been taught this factor label method, okay? So I got kilometers, so I have kilometers here. What am I going to put down here?
Kilometers.
Kilometers, okay? And then I want to put meters up here. 1 kilometer is 1,000 meters. So I'm going to write that as 112,000 meters. If you like scientific notation, which I do in this case, I'd write that as 1.12 times 10 to the 5th meters. Okay? If you don't like writing times 10 to the 5th, some people write 1.12 e to the 5th. Okay? That's cool. Either one. I don't care.
Make sure it's big E.
Huh?
Make sure it's big E.
Yeah, no, not little e. So I don't care which one you do, okay? Doesn't make me any difference. So that's one conversion. The other conversion you're going to do is that let's say that you're going 120 kilometers per hour, and you want to change that into meters per second. So this is going to require 2 different conversions. So here's how, and this, you are going to do this so often, I want to make sure everybody's cool with how I want this done. That's 120 kilometers per 1 hour, okay? That's what that means, it's 120 kilometers per hour. Bank this hour down below. Then, I always do the first step, put 1 kilometer, that's 1,000 meters. So that's good. If I stop right now, I get meters per hour. Now, to give you some perspective, 120 kilometers per hour is about 70 miles per hour, okay? Just kind of a ballpark idea, okay? Now, what I would recommend, and there's 2 ways that you can do this. You got to put the 1 hour up here. So, if you have 1 hour, how many seconds is that? Okay, hold on, y'all have been out of school. So 1 hour is how many minutes?
60.
60.
60 minutes. 1 minute is
60 seconds.
60 times 60 is
306. Yeah.
3,600
Yeah.
seconds. Not 360, this isn't degrees in a circle, okay? It's 3,600. So that's 3,600 seconds. So the hours cancel out. So here's the shortcut version. This is if you're doing this without a calculator. You can actually like lop off a couple of zeros. So the shortcut version, if you change them from kilometers per hour into meters per second, just multiply by 10 and divide by 36. Okay, this is the only thing that changes is what you put up here. So it's always times 10 and divide by 36. So go on, do this. Take 120 or 1,200 and divide that by 36. So 33.3, and she gets 33 repeating 3, but I'm only going to write that as 33. And the only reason I'm going to put this as 33, technically your calculator is going to say it's 33.3333333. Well, written like this, as 120, there isn't a decimal place. This only has 2 significant digits. How fast were you going? I was going about 120, okay? So I convert this, it's about 33 meters per second. I got sketchy data, 2 significant digits. My answer can only have 2 significant digits. Now, the other thing that you will always see when you convert from kilometers per hour into meters per second, this is a little self-check that you can do. Because you're multiplying by 10 and dividing by 36, this answer always has to be smaller than what you started with. So if you convert kilometers per hour into meters per second, and you get a bigger number here than what you started with, you did something wrong. This always has to be smaller than what you started with. Okay? Okay, so, okay, so let me explain how I want assignments done, like or out of the book or when I give you problems to work. So, this is going to be assignment 1-1. So when you guys scan this and send it in to me, this is what you're going to call this thing. It's assignment 1-1. And this is on page 24 out of your book. And you have problems 14, 16, 18, 20, and 21. This is, by the way, if you've checked your email, I sent you like a revised schedule. This is on the PDF file that I sent out, okay? At the end of every chapter, you have two different categories. You have questions and you have problems, okay? So these are all out of the problems section, okay? So pay attention to where you're coming from when you're doing these. There's the problem section and there's the question section. These are out of the problem section. Now, here's how I want this done. Make this easy for me. So like, here's your sheet of paper. Okay? So what I want you to do is come over about maybe 1/4 of the way, a couple inches. And I want you to draw a line down like this. So like a number 14, there's 14 part on 14, there's 4 parts to it. So you can put like 14A. What I want here is the answer to 14A. Over here, I want this, these are just conversion problems, these are pretty simple. So over here, I want the work that generates this answer, okay? So you can put 14A, boom, for example, on this one, you're converting like microseconds into seconds. So you're gonna have a conversion here from microseconds into seconds. Have the answer right there. Now, the next one is going to be 14B. So what I want the answer to be here, and then I want the work here. Don't stack the answers up here and then have that work running down here. View this from my perspective. I want to be able to look at this answer, and then over here I want to see the work that generates it. Okay? So keep this answer here, right beside it. When in doubt, leave spaces, especially because you guys are going to be taking pictures of this. Don't cram all of this work into one big massive thing where there's no gaps in between it. That is going to be so difficult for me to grade. So what I would recommend is that you do 14A and then maybe leave like a gap, like a line in your paper, and then do 14B. So when in doubt, leave a gap, okay? So then you're going to get down to like number 16, you can do the same thing, 16A, boom. So don't try and cram these answers into small spaces. Move, have this line over quite a ways. Some people freehand this line, some people draw it with rulers, some people go nuts and they'll like scribble and put stars and everything in between. You don't have to go to that extreme. But just again, visually look at this from my perspective. I'm going to have 17 of these to grade, leave a gap. So here is, and by the way, read chapter 1. It talks the rules for significant digits. Those are there. It's got the conversions. So here's this assignment's going to be due tomorrow. So again, on assignments, I want them by 6